Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. Let's continue with the different kind of flexure mechanisms, and today we'll cover flexures in tube walls. So if we take a tube and with a very small thickness T, what we realize that we can create different kind of compliant mechanisms with the different degrees of freedom and constraints and range of motions. So for instance, if we take this case, so hollow tie rod, so thickness is really small here, and the other parameter is h, the width. What we have done here is, so we can make cuts, soft cuts, and we can also use hole flexures in this case, and between the two sections we also create a width h. So what we realize that if we at each end, if we consider this end and this one, at each end we have created two perpendicular tilt axes. So for instance, in this case z and x direction. So if the axis is y axis, the longitudinal axis or the center line of the tube is y axis, then xz is the plane. So what we realize that we can create different kind of flexures, and here if you create two perpendicular tilt axes on the either end, actually we create double inversal joints. So at the end 1 and 2, and then we can create a very good mechanism here. What we also realize that if this h, if it has a high value, so width is large, so that section will be rigid, and therefore the y stiffness will be very high. And of course, if we check this arrangement, what we also realize that the rotation along the center line is also constrained because it has a huge stiffness. So if you take this tube, the constraints are basically the translation y and the rotation psi about the center line. So rest all four dots are 4 degrees of freedom are there, except that translation y and the psi along the center line. What we also realize that these two parameters h and t, they are very important, and the stiffness of this, the constraint direction y and psi, it depends on these two parameters h and t. So depending on how we choose these parameters, what is the thickness, what is the value of h, we can get different degrees of freedom and constraints. So one of the application of this kind of tube flexure is concertina bush, and what we see here that this h is very small, and This is even compared with this T. So T is quite large with respect to H. So it's a thick wall. So this bush we can call thick wall bush. And what we realize that in this case, just the shortcut and two perpendicular axes we have created, and because of that, since the H is small, so the stiffness along y direction is quite a small. So that will be degrees of freedom, and other degrees of freedom for this kind of arrangement. What we see is theta and phi rotations. Psi is here constant because it's along the center line. So if we have this kind of arrangement, what we achieve is the compliance along this direction, or we can say low stiffness in y direction, theta and phi. So low stiffness means large compliance, so it can move. At the same time, the constant directions are this. It's quite obvious. In x and z direction it cannot move. Similarly, the rotation, since it's a thick wall, so T is substantial, so we cannot rotate along the center line as well. So we'll get this high stiffness along these directions. So what we realize, since in the stiffness in y direction can be manipulated using this H, so we can create a kind of preloading along the center line, and this kind of arrangements are used for pre-stressing components along the center line. So if you want to design something so that we can press anything inside, we can use this kind of arrangements. So very good application is for making piezo stacks, and if you are aware, you know that for piezo materials, it's a very important to have preloading to get rid of hysteresis. So we can use this kind of arrangements, so alternate cuts, and the H is chosen in such a way that when we tighten it from the ends, so we can compress the tube and tube get extended and the material will get compressed inside, and that is a very useful method in designing these kind of actuators. So from the tube we can do many kind of designs. So for instance, angle transmitter bush. So if we can consider again a tube and make a cut like this, what we realize that we create two sheet flexures, and in this case what we realize that only constraint what we have is phi. So the connection is stiff in torsion. So if you try to twist the two end A and B, they are connected via the element C, A and B, the two ends, and they are connected through this element C through these flexures F1 and F2. So it acts like a sheet flexure, and it's mainly because the thickness parameter here you can see is large compared to this width H. So it's more or less like two sheet flexures, and we can get a very good flexures which is connected in rotation, or we can say constrained in rotation, and it can be used for angle transmission. Similarly, we can take the tube and we can also create a straight guiding flexure mechanism, and as is evident from here and from here as well. So we can pull the ends, so we can, there will be displacement in this direction, but yes, it cannot bend. So it's a straight guiding mechanism. And if you really want to see, you can see if we just wrap up and then try to, so it's like sheet flexure and try to flex. So these pairs, if we see, so 3 pairs are there, and then if we try to pull, these flexures will deflect and we get a straight guiding mechanism behavior. So very nice, I think, and can use these tubes to design different kind of flexure mechanism, even for common use. So very important topic, another topic with respect to flexure is negative stiffness. Usually we don't talk about negative stiffness in mechanisms unless we are talking about bistable mechanisms where it's switching from one side to other side. So we'll try to understand what is negative stiffness and what is the importance of such mechanisms. So just to illustrate, if a person, if there is a spring here and the force is applied, what we see is force versus displacement, and we see this behavior which is positive. So the force, direction of force and direction of displacement is in the same direction, and that's why this is a positive stiffness many times we refer to, and in most of the cases we encounter this kind of behavior wherever we are using springs or any kind of elastic mechanism. If we are using, generally what happens, what if suppose certain load has to be lowered along this direction and there is a slope, but we realize that we have to always apply a force in this direction, although the displacement is in this, in the x direction. So for positive x direction there is always a negative force applied, and if we just try to see here, what we realize that the force versus x plot is negative downwards. So for any, so you can see that even for some displacement there is always some force applied in the negative direction. So many times difficult to visualize, but um, we can always think of the direction when we have to apply a force in the negative displacement direction. It means there is some kind of negative stiffness involved there. So what happens if we combine? So if we combine this, so suppose lower this thing in the ramp and then connect this part with this spring, what will happen? So of course these two stiffnesses will be added, and what can happen that if it's finely tuned, if both K positive and negative is matching, we, in a way we can get a zero stiffness. It means we can place it anywhere and it will stay there. So because the forces are balancing each other, so whatever forces, because of the positive and negative stiffness, they are balancing each other, and that's why it's a stable at every location. So this can be very good because we can combine the positive and the negative stiffness part, and we can tune the overall performance, the stiffness of the system. And many times, suppose if you are looking for zero stiffness so that it can stay anywhere, or for many vibration isolation cases, or even for some behavior vibrational characteristic, we may want to have a very small k, and for in those cases it's a very difficult to directly design something with a very low stiffness. But if we combine the two, we can get a near zero stiffness kind of things, and we can fine tune the vibrational behavior of the system. In flexures, in compliant mechanisms, what is good about it is the negative and the positive stiffness is intrinsic to the flexure, so it's already there because it's an elastic mechanism, so the positive stiffness is already there. And with some arrangement, if we are able to get that negative part, so for instance in this case if we apply a load n, and since it's moving in this kind of ramp, so there is a negative aspect. So more or less if that is the arrangement, what we realize that parallel guidance with the negative force can give us some negative stiffness, and we can, depending on this force n, we may be able to fine tune it and then achieve near zero stiffness. So in compliant mechanisms or in flexure, what we realize that some of the things which is not desired can be still used, and for instance in this case the buckling. So how the buckling can be used to get a negative stiffness, and so what we can see, if L is the length of the sheet flexure or valve flexure, and if it's preloaded by delta L, so that it already get buckled. So it's already, because it's already compressed, so in order to accommodate that delta L, it has to deform, so it will get buckled. And what we also realize that buckling, so most of the time we talk about the fundamental mode, so the first mode, but there can be various modes also. So for instance this case also, so other modes can be also possible depending on how we manipulate. And if we control, we can get higher modes, and accordingly we can get a different stiffnesses values. So for instance in this case, for this case, this is the stiffness, and you can see the range of motion is very small, so it works only for a small range, and it's magnified now. So that is the displacement range we are talking about, and in that range we'll get a negative stiffness because we have to always apply force negative to the displacement required. So of course you don't have to remember the formulas. If it's required, we can always uh, refer to the relevant data or the formula, and if you want to learn more, we can refer to the literature. So but what is important to understand, that if it's already preloaded and in buckled shape, the stiffness is negative. So if we see this case further, what we realize that if we go for different modes and control the angle at the center, we can also play with the C values. So by default for this arrangement, this is the stiffness value, minus value. But if we twist it and try to manipulate, this C can be changed, and that's how we can fine tune the vibrational behavior of the system. So very good example here from University of Twente. So very nice demonstrator. So you can see here sheet flexures, but here you can see it's already uh, buckled, so pre-stressed, and from here actually you are controlling the center part, so by tuning. So now you can see the frequency is higher, so it means K is high. But as you were tuning it, and the positive and the negative stiffness tuned, what you realize that the free vibration mode, the fundamental mode, is really small. So if we just compare with under root K by M, the stiffness under root K divided by M, so the K is near 0, it means that omega can be very small. So very nice demonstrator, and is from University of Twente, and uh, the most of the content what I'm referring to in this lecture or in the compliant mechanism lectures is from the Professor Sumer's book, from Design of Precision Mechanisms, and this is one of the demonstrator from there itself. So we should be able to appreciate how it can be tuned and can be used for different applications. So what are other ways? What are the different ways? So the pendulum and inverse pendulum case is very obvious. So this is stable. But if we just invert it, what we realize that it always tends to fall. And in order to support it, we have to always apply a force in the negative direction. So the inverse pendulum can is a case of negative stiffness. So simply reverse the pendulum case. So if we reverse the forces, we may be able to get that. So just to get some idea, and how the preloading can also bring negative stiffness in certain directions. So suppose if we take a bar hinged at this location and we just apply a preloading vertical direction FB, what we may ask, what is the stiffness in this direction Cx, whether it's a positive or negative. So if we try to analyze that, but we realize that for very small deflection dx, these are the forces acting. So Fb, and this will be the force required, and this is the force coming on the link. And for very small angle, if we just do the force equilibrium and try to calculate, what we realize that in the fx direction, this is the force what is required to give that displacement dx. So if we try to calculate and find the stiffness, so we can imagine that is stretched with the or a tensile load Fb acting downwards, and we try to pull, yeah, we can feel the stiffness, and that stiffness is nothing but this the force Fb by dx by L. So we can always use trigonometry, and when dx is very small, then this can be, so that's why we have, so tension will be almost equal to Fb, but this number will be dx by L, and this can be cancelled, and ultimately this is the stiffness we feel, Fb by L, that is the stiffness in the x direction. Of course, this is positive in this case, and another way to also check is the pendulum frequency. So if simple spring and mass system, if we consider Cx by m under root, and Cx, if we simply replace Fb by L, which is your, so if it's a simple mass and under gravity is mg by L, and if we put m will get cancelled, and then we are left with under root g by L. So it's a well known, and I think it matches with what we are getting here. So we can be very comfortable in using this formulation. So just remember, if there is preload Fb working, the stiffness in the x direction will be Fb by L. What if it's a compressive load? So if it's a compressive, then the direction will change. So it will be negative, as we saw in the previous case. So in the previous case, so the pendulum and the inverse pendulum. So likewise here, if we just reverse the direction of this force, now what if is in this direction? So if direction is changed, yes, here we will get negative stiffness. So as we move on, and just consider a cantilever. Now it's not hinged, but it's a cantilever beam, and if we apply a force Fb in the negative direction in this case, so what are the forces and what are the stiffnesses values? So for instance, we are interested in the total stiffness in this direction. So what will happen? So there are two stiffnesses working. One is the stiffness because of the reloading, this thing, and the other is the bending load. So F will try to bend it, so positive stiffness, so Cb, which is in this case for cantilever is a 3I by LQ, which is positive. We have to always apply the force, but because of the arrangement and what we have seen earlier, if we apply a negative force or force in compression, Fb by L, this is what we got, and since it's a negative, it's a minus, so minus sign is there. So we see a very good arrangement here. So there is a positive stiffness, which is because of the bending, and there is negative stiffness because of the nature of the force, because of the preloading in the negative direction. So if we preload, we'll get negative stiffness, and because of the bending, we will get the positive stiffness, and if we fine tune, we can get a near zero stiffness. So this CTR, which is the total stiffness of this member, is a function of Fv as well. So this is for a compressively loaded flexure. So it's a simple cantilever. What happens if we guide the end? So yeah, so in many cases what happens, they are not working individually, but the flexure members, we are combining them. So for instance, parallel guidance mechanism, those kind of application, the ends are guided. So we have very much this kind of situation. And in this case, if we analyze, I think what we have already obtained, that the stiffness because of the bending with these boundary conditions, end conditions, is a 12 EI. It's not 3 EI by LQ, but 12 EIQ. Again, this is the positive stiffness. Because of the negative part, negative FV will get the negative stiffness. So again, we can, the total stiffness we can control, the positive part and the negative part, and we can add it, and we can fine tune it comfortably or based on our application. So another case where, suppose if we preload, so for instance, we can easily compare with the bicycle stand. The older bicycles have this kind of spring preloaded. So you can just imagine the inverted case, and okay, you have a link and then it's connected through a spring on the other side, and we encounter that bi-stability, so it stays on this side or the other side, right? So these kind of mechanisms we can easily analyze using potential energy concept, and yeah, we can write all the equation, what are the potential energy stored in the spring with respect to the displacement, and of course the force and the stiffness we can calculate. We are not going into the details of how we arrive it, but we might be interested in the is the stiffnesses values, and this is the arrangement. If this C is the stiffness of the spring, and preloading the member, this member, at a certain distance below, what happens. And now if we compare, it looks very similar. So this is the spring which is preloading these flexures, the sheet flexures we can call it. So we have the flexure parallel guidance, and with preload, and whether we can get negative stiffness in the x direction, C total. So again we use the potential energy formulation, and if we take the first derivative, we get the force, and then second derivative we can get the stiffness. And what we realize that there is a term with minus C delta L, and under bracket 1.21 by small l minus 1 by capital L. And so what we realize, this part, the negative stiffness, that behavior we will get only if the values in the bracket is positive, because negative already we have taken out. So 1.2 divide L minus 1 by capital L has to be greater than 0. And if we, and of course this is the positive part, which is because of these two flexures. So if we just work out this, what we realize that 1.2 L greater than 1 by L, and out what we realize that this L has to be larger than L divided by 1.2. So okay, certain fractions you have, but what we can always say that L has to be always larger than this L. So some 0.8 or something, but yeah, rule of thumb, what we can say is this L has to be bigger than this L. So it has to be below. Otherwise, we cannot get this negative stiffness. So it has to be below, and then only we'll be able to achieve that negative stiffness. So that's something we have to remember, keep in mind. So if we want to have a stiffness or a parallel guidance mechanism with the negative stiffness or a stiffness near towards 0, then we can always combine. So for instance, it's a flexure parallel guidance you have here with preload. So preloading is because of this. So preload for negative stiffness in x direction. So this is the x direction, and so that we can get a functional parallel guiding. So here the C total, because there are many parallel guidance. So one is here, another is here. So we have to put everything together, and we can see what is the C total we want, and we can calculate accordingly. So we have learned a lot of mechanisms, and also learned how to play with the stiffnesses values. So there are many examples, and as we move on, we may realize that there are different kind of flexure mechanisms reported every day in literature. There are a lot of patents. While teaching this course at IIT Delhi also, with working with the students, working on different new application, we come up with very new designs using these flexure mechanisms. Elsewhere also, people have been trying and coming out with very novel and very new designs. but the basis is the same, what we learn, and there are many literatures, but this is what I'm referring to, Professor Sumar's book. He was my supervisor also when I was doing my PhD, and thanks a lot to him. I learned a lot from him, and he retired from Philips. I also learned from Professor Dennis Brower and Professor Yesterday from Delft and Twente. So they are teaching this course in Netherlands. There are many people working. There are many researchers in UK also, in USA, Cranfield, MIT, in India, Professor Anand Suresh. So there is a dedicated course on compliant mechanism itself by Professor Anand Suresh. It's available on NPTEL. So there are a lot of literature available these days. And what we realize that if we try to design machines for precision applications uh, to support any kind of initiative, semicon industry or semicon mission we have, or want to develop systems for a space application, ISRO is there, or if we want to design systems for um, some particle accelerator and those kind of programs, or design systems for optomechatronic applications, what we realize that these are the basis, and using these fundamentals we should be able to create new designs, we should be able to develop new machines and instruments our own. And uh, of course we have the confidence, and what we will also learn is what are the other elements. So for instance, the friction is one of the problem we have to deal with. So we also try to find what are the issues with the friction and how to mitigate that, so that the control burden can be reduced, the control effort required can be reduced. So precision mechanism in general, or design for precision, it cannot work alone by using mechanical design. It has to be always work with, we have to work with the mechatronics required. So control, the actuator, sensors, the compensation, adjustment, all that has to be there. With mechanical design, with the focus what we are covering in this course, what we can do is we can reduce the randomness in the behavior. We can design a deterministic setup, deterministic system, so that all the systematic noise or systematic error that can be compensated later using proper control, electronics, actuators, sensors. And of course many times we need to work with the stiffnesses values, so that we can understand what is the bandwidth, what is the requirement, whether we want to work in the low frequency part or the high frequency part. So depending on the application, sometimes we want to target very fast and uh, quickly maneuver and reach the location. So for those kind of application, we may need to have a very high stiffnesses values. But on the other hand, suppose if it's a kind of a very sensitive equipment designing for different applications, or suppose we want to support something and don't want to transfer any kind of vibration or noise from the ground also, then it has to be supported with a very low stiffnesses values. And therefore it's a very important to understand what is the application, what is the requirement, what are the precision requirement, what is the bandwidth, what is the frequencies we are looking at. And depending on the application, I think one should be able to find out and understand what are the degrees of freedom required, what are the range of motions, what are the degrees of freedom required, and what are the constraints required, because over constraint can lead to a lot of problems and we may want to eliminate. So therefore, in the next lecture, in the coming lectures, we'll be talking about other problems, the frictions, the dynamics, and later we'll be also talking about some case studies, what we have worked on, or even from the literature, if we have some good problems, we'll discuss about that. So let's continue and continue with the next topic in the next lecture. Thank you.